when you have a 9 cross 9 filter of the kind that we had, that I had shown. Let me see if we have that here. Something like this, right, is what I had told you. The approximation to this, to the kind of true log, right, looks like this. Oops. Okay. So the approximation rate looks like this, and okay, I think something got shifted anyway, it doesn't matter. And then your dxy rate looks like this, and I was asking you, can you still use integral image concept to be able to compute dyy, dxx and dxy? That was the question. How do you solve this? Hitesh, how do you compute using integral image? Something like this. So it's like this, right? I mean, I'll just give you an indication about how to kind of go about doing this. It just requires a shift of I sigma. Just requires I sigma to be shifted up, down, left, right. That's all it takes. For example, think about this. Okay, let me take the same example. I'm just going to drop hints now. Okay, because you guys should also do your part, right? So this is what we had: 1 3 2 4, 5 2 1 6, 4 6 2 5. Okay, this was I, and then 1 4 1 1, right? This was the example that we had taken, and for this we got an I sigma which looked like, because it had zeros appended to it, and then 1 4 6 0, sorry, 1 4 6 10, I think, 6 11 14 24, 0 no, sorry, 10 21, 26 41, and then 11 26 32 48, 32 48, and then we had appended zeros on the outside. Okay, this is what we had, no? How to get it from I sigma? No? Okay, so it's like this, right? So imagine, for example, suppose I had a filter like this: 1 1 1 1 1 1 minus 1 minus 1 minus 1. It doesn't matter. The third row could have been minus 2 minus 2 minus 2 for all I care, right? But then it's like one sort of box, another box, another box, and so on. So now what you can do is, you can actually think about having two box filters now. One is this guy, another is minus 1 times this, right, which is like 1 1 1. Okay, and the idea is that you want to be able to use I sigma to be able to do everything. I don't want to go back and recompute anything, right? Then it's like your usual thing, which we know how to do. So suppose I sit here, right, and suppose I apply this 1 1 1 1 1 1 minus 1 minus 1 minus 1. I should get, what should I get? 6 plus 2 9, 15 17 22 minus 6. I should get 16, right? If I convolve at this location with that kernel, my answer should be 16. Okay. Now the point is, right, if you actually keep this kernel here, right, then with respect to the box filter 1, right, if you try to compute what your ABCDs are, right, so your filter will sit here, right? If you take the top box, which is a box 1, right, and your center is here, right, for that filter. So actually keep that here, right, then your A, okay, will then be what? Your A will be 1, right, your B will be 10, C will be 24, huh? No, C will be 10, C will also be 10, right?
C will be 11.
Why 11? You are sitting here, no, C is this guy, right, on top of 24. Why C 11? I am sitting here. C is 10, and D is 41, right? So now if you do A plus D, that's 42 minus 20, which is equal to C 22. Okay, now if you convolve 1 1 1 1 1 1, you should get actually 22. 6 plus 2 9 plus 6 15 plus 20 plus 2 22. Okay, now with respect to the other one, minus 1 minus 1 minus 1, one way to kind of, right, think about it is to actually actually shift this, see, because minus 1 minus 1 minus 1 is going to act on 26, 32, 48, right, or in other words you can think of I sigma being shifted. Either way, right, either you think of minus 1 minus 1 minus 1 acting on, but then that is not the way you want to do it, right, you want to do everything with respect to I sigma. Show that, right, I mean if you were to take minus 1 minus 1 minus 1 and all that it requires is for you to kind of shift this I sigma up and then do this A plus D minus B plus C and then take this minus that and that will give you that 6. I mean you can right away see, see for example if you take minus 1 minus 1 minus 1, that's it's here. So if you look at your A for that, right, that is like 10 and then B for that is 41. Right, C for that is 11 and then D is 48, right. So, what do you get? 48 plus 10 is 58 minus 52, right, that is 6, which is what you would have got 4 plus 2, 6, and now you do 22 minus 6, that is 16, right, that is the answer here. So, all that it requires is for you to able to shift I sigma and simply do this A plus B on the one for one box filter, then this A plus B minus whatever A plus D minus B plus C for another box filter, subtract the two and you have the answer. Okay, now let us kind of move on. Okay, now to come now let us kind of look at how the okay, Renish, what you are not convinced or convinced?
Yes, sir. I need to try it.
Yeah, try it out. I mean it's not any great rocket science, right? Okay, now so let us come to this key point courtesy detection. Oh, okay. Yeah. Prior to that, right, there is something else, okay, which I have to talk about. Now, similar to the SIFT, right, you need this what do you call this kind of an octave thing, right, even here. But then, right, I mean as I said, right, so what these people do is they can actually go for right any size, right. I mean so in that sense, right, they have that disadvantage. But the way, right, this is done is you take the first octave. So, this is the actual implementation, it goes like this. So, you call this as octave 1, okay, and there is a certain kind of reason to start like that. Okay. So, for example, this I said is a 9 cross 9, okay, so I will just write it 9. So, the first size, right, I said that was corresponding to sigma equal to 1.2, right, that is the minimum at which you start your approximation of the log or the dog with a box filter. That is that minus 2 1, that approximation, right, which you made. Then what they do is, right, the next one is at actually 15. So, it is like in one octave when you go up the scale, right, there you went like sigma, k sigma, right, k square sigma, that is how we went, right. Now, here we do not have a corresponding k, but instead what you have is a jump of 21, right, 21 and then 27. Okay. Now, there is a certain reason, right, why basically, right, this is done. Actually, this actually, I mean, in order to completely understand this, we need about 3 to 4 classes. Okay. If you actually go through the exact analysis as to what a true linear Gaussian scale looks like and what approximation, right, will kind of bring it best to a box filter, and then what will actually preserve the energy in the Gaussian, whatever is the energy there, how will a box filter version preserve the energy. So, a lot of calculations there. Okay. One needs about 2 to 3 classes just for doing that. We can't afford that, right. So, what I am going to do is I am just going to tell you briefly as to where these things emerge from, so that, right, you get a rough idea as to how this happens. So, the second octave, right, I mean I will first write down, okay, and then I will tell you how this comes. Second octave starts from, where does it start from? Yeah, 15, and then here it's a jump of 12, okay, 27, then I am not drawing to scale, okay, 39, then 51, and then octave 3, right, goes up like this starts from 27, and then here it's a jump of 24. So, it's like 51, what is it, 75, yeah, and then 99, and then, right, you can have further octaves also. Now, the idea is that right, I mean you I mean since the computer even at 99 cross 99, there is no big deal, right, to do the computation, because everything can be done with just the integral image. All of these can be done with integral images. Okay. Now, they still want to use octaves simply because, right, I mean if you keep, right, I mean expanding the support, right, then you can actually catch them early on. the spacing, right, that you have here. See, one I said that, right, this is like sigma is equal to 1.2 approximately. Okay. This 15 and whatever this 27 are all chosen such that the midway sigma at either extreme. Okay, that means if you compute between 9 and 15, right, you got like 12, right, and between 21 and 27, right, you got like say 24, and this jump of 6 comes roughly for a k of root 2. Okay, this jump of 6 pixels in the first octave, right, you can roughly think about, for example, right, if I compute the sigma here, okay, this will be like this will be like 1.2 into say 15 by 9. Okay, that sigma if you calculate it, it will be roughly root 2 times that 1.2 that you had in 9, roughly. Okay, it's not exact. None of these calculations is exact. Okay, these are all approximations. So one way to think about it is the sigma here and the sigma here, right? It's like almost covering one octave. It's like, you know, you have like, you know, like you have covered a whole sigma, right, in going from 12 to 24, because you had whatever sigma here, you'll have say twice that value of that sigma here. And similarly, right, if you go here, okay, this one will be like what is this, 15 to 27 means 21, huh? So you got the mid one is 21, and here it will be 45, right. Now 21 times 2 is of course not 45, but it's roughly like that, right. So in every octave, the mid sigma value at both extremes, right, are such that you cover roughly 1 sigma, okay, across that octave. And when you actually when you actually go up, the jump is by 2, because you know, that's called a dyadic sampling. I don't know whether I used the word dyadic, right. So when you did that dog, right, we used to go up by, let's say, right, 2 sigma, right. So here the corresponding here, because there is no notion of sigma and all, the notion is in terms of the spatial resolution. So you kind of go up by a spacing of 12, then you go up by a spacing of say 24. That is to say replicate to some extent what you would like in a kind of, you know, dyadic sampling to happen. Okay, and again, right, this will be like whatever is the center thing, right, it will be roughly this, and this value will be roughly, for example, roughly see twice this. Like I said, it's not exact. See, when you go up the next scale, right, you expect a 2 sigma to enter, right. I mean, it won't be exactly 2, but 12 times 2 is not 24, it's like 21, but that's the because it is all a discrete approximation, so you won't get anything that's exact in terms of a continuous case, but you can roughly think of, for example, even here, right, if you go 27, 51, what is that? 34, right? No, 27 to 15, what did I say there? 39, right? This will be 39, correct? This mid value. So 39 is not, of course, 21 2s is not 39, it's 42, but 39 is still close. So it's like, so you go up by so this mid sigma at both extremes are such that when you go up, they go up by a factor of 2, and when you go along the octave, they go up by a factor of 2 if you check the 2 extremes, the midway extremes of the sigmas. Okay, this is roughly the kind of the scheme, and within the scheme you have to now find out. So right, think of this as analogous to the way, right, you were doing you know, a log approximation. Okay, but now since you have that filter already, right, you have the dxx, right, which I showed you already have what that filter should look like, right, dxx, you had dyy, and then you had whatever, right, dxy. So you have these things at whatever size you want. Okay, they are there, and right, all that you need is wherever whatever size is needed, you just have to apply it at that size, and then similar to the earlier case, right, we have to now find out where the extrema are, right. I mean, that's what we did there also. But now the point is, how do you pick the extrema now? Right, what should flag whether something is interesting or not, and there what were we doing? I mean, right, wherever we are, we used to check a 3 cross 3 around it, and then we used to check a 3 cross 3 above it, and the 3 cross 3 below it, right, around 26 neighbors, right, 26 neighbors. So similar to that, we have to do here also. So it's like, it's like, okay, check here and then check above, check below. Now in order to do that, right, so here what they do is so in SIFT, right, because anyway, right, I mean, you've gone for a kind of a box approximation. What is done is the following. So you have like h, okay, I mean, x comma sigma is what is written, but of course, typically it should be x comma y. So this ideally, right, is this matrix Lxx of x comma sigma. Actually, it should be x comma y, okay, Lxy of x comma sigma, Lxy of x comma sigma. This is Hessian Lyy of x comma sigma. Okay, this is the Hessian. So, each of this is actually a second derivative. This is the second derivative. So, second derivative of the image I, which you can compute using this approximation that you have with you, dxx, dyy and dxy. At every point, right, you need to actually compute. You will have, right, if you do just one convolution, you will have all those values. It is not like you do it individually, but whatever, right. If you are sitting at a particular location, then you have the Lxx value for that location, you have the Lxy, you have the whatever, right, Lyx, which is we are assuming to be same as Lxy, and then Lyy. And then what they do is to check the strength of that particular response, right. I mean, you need to know whether that point should be considered as important or not. So, what you do is the actual thing that is taken, right, to actually check the significance is actually a determinant of h, and that is computed as dxx into dyy minus 0.9 dxy square. Okay, now, where this dxx is all an approximation of Lxx. I mean, Lxx is actually the I mean log, the actual log which you would have ideally liked to have there, but you do not have that. So, you have an approximation of the log through a box filter, which is dxx dyy. Okay, yeah, right. Do not get unduly worried by this 0.9 business, because this 0.9 is coming out of, like I said, right. So, when they actually equate the this one, right, energy in the true sort of a Gaussian, and they try to equate that energy with respect to that of a box filter, they want to make sure that the energy remains the same. So, this 0.9 factor is coming from there. Okay, like I said, the derivation of that is is kind of beyond the beyond this course. But why does this make sense? You tell me. Let us see, right. You guys have an exam next week. No, yeah, next week, right. Yeah. So, why does this make sense? A determinant of h. So, if this is a high value, right, I take it to be right, I take it to be a strong response. I mean, I'll get a value, and of course, I can do the same thing, right, which I would do, like 3 cross 3 compare and all that. But first of all, why does this make sense? Forget about the 0.9 and all. Okay, let us not worry too much about that. A determinant of h. See, what he is saying is, after all, a determinant is simply a product of the eigenvalues. Okay, and if you do a Taylor series expansion, right, about, let us say, right, if you think that you are already sitting at the optimum and you are just trying to search around it, right, and you know that if you are actually sitting at the optimum, then if let us say x transpose, right, if x transpose hx, right, which will be actually one of the terms, right, in your, or let us say h transpose whatever, right. I mean, let us say if it is delta x. Okay, if you're taking a delta x kind of a deviation about x, and you actually believe that x is the optimum, then the first derivative is anyway 0, right, if it is an optimum. Now everything hangs on this h now. Now, if it turns out that if h is actually a PSD, then what it will mean is, right, that this number has got to be greater than or equal to 0 for all right, I mean, for all of this the delta x, right. So, it should be greater than or equal to 0, which then means that all the eigenvalues are actually positive, right. So, all the eigenvalues are actually positive. That you can show by taking, right, delta x to be if you just take that to be the eigenvector, then you can show that h delta x is simply lambda delta x, and therefore, delta x transpose delta x is greater than or equal to lambda greater than or equal to 0, right. So, it actually means that all your eigenvalues are actually greater than or equal to 0, which means that actually you are actually sitting at this one local minimum, right. You're sitting at a local minimum, because any deviation from that is actually increasing the function value, correct. Whereas, if on the other hand, if you find out that at some point, right, where you're sitting, if delta x transpose h delta x turns out to be less than 0, let us say, or less than or equal to 0, right, then we know that your eigenvalues are all actually less than or equal to 0, right. But then if you take the product, right, the product will still be, but the product will still be a positive number, right. Okay, so so it means that, right, either way you go, right, either way you go, I mean, you will actually end up with the fact that whether it is PSD or it is NSD, right, I mean, a negative semi-definite or a positive semi-definite, this number, right, will always kind of indicate to you the strength. But if you had, let's say, any other, if you are sitting anywhere else, right, then okay, then right, then of course, then your H is not, it's not either. In which case this number, right, will not it will not kind of indicate a kind of local extremum. The idea is to be able to catch the extremum, right, a local extremum. So the local extremum can be caught by using a determinant of H. Does that make sense? Okay. So then what you need to do is, so in order to be able to search for it, right, so in order to be able to search for it, so in order to localize, okay, now let me just write this down. Okay, in order to non-maxima suppression and a 3 cross, okay, in order to localize points, so you have the strength, right, at all the points. In order to localize interest points, in the image and across scales, right, in the image, that means at that octave and across scales, I mean across scales as well as octave. Okay, across scales actually typically means, along the octave. A non-maxima suppression and NMS is in a 3 cross 3 cross 3 neighborhood, right, that is the same as what we have seen before. Neighborhood is applied. The maximum of the, say, a determinant of the I mean Hessian is taken to be this interest point, or taken to be the key point.